Good afternoon, everyone, and welcome to another theoretical physics seminar for 2024 on behalf of the Australian Institute of Physics. I'm Dave Tilbrook from the Department of Fundamental and Theoretical Physics at Australian National University. Our previous seminar, which was presented a couple of weeks ago, was by Professor Archil Kopanais of the University of Sydney. He gave a fascinating talk on a theoretical approach to global topological features of the vacuum states of relativistic quantum systems, and he described some new phenomena which might be amenable to experimental verification. As I said, it was a very good talk, interesting talk, and if you'd like to see that, it's available on the AIP YouTube channel. Just do a search under Australian Institute of Physics on YouTube and you'll go straight there without any difficulties. So just before we do some physics, a couple of quick reminders to everyone. The 2024 Australian Institute of Physics Congress this year is being held between the 2nd and the 5th of December at the Melbourne Exhibition and Conference Centre, I believe is its correct title. Abstract submissions for that Congress have already closed, but you can still register for the conference if you'd like to attend. I forget what the pricing is. There's a range of pricing for staff, students, retired people, and so forth. That information is on the website. If you want more information about that, just do a search on aipcongress2024.com. That's one word, AIP Congress 2024. It's a congress which many people might know, which covers a broad range of physics, so there's something of interest for everyone. The other conference to mention is the upcoming 47th Condensed Matter and Materials meeting, which this year is being hosted by the University of Queensland. That's being held from the 4th to the 7th of February 2025. Now, the registration for that, if you'd like to attend, doesn't close for quite some time. It's open until the 15th of December. So you've got some time. Abstract submissions, if you're thinking about submitting a paper or a poster if you're a student, you might want to think about doing that. It's a very good conference for condensed matter physics. It's a relaxed conference, and it's one that's been running for a very long time, many, many decades. It's the main conference for condensed matter physics throughout Australia, probably Australasia, in fact. So if you're thinking about you want to do a paper or a poster for that, now's the time to start putting something together. Okay, so our speaker today is Associate Professor Karen Livesey from the University of Newcastle. Karen is a theoretical condensed matter physicist carrying out research on magnetic nanomaterials. She graduated from the University of Western Australia before working at the University of Colorado Springs, after which she returned to Australia in 2020, which is good for Australia. Karen has been presented the Women in Physics Medal by the Australian Institute of Physics and a citation by the Australian Awards for University Teaching, both very good awards to win. Karen is also, this is, I think, very interesting and very timely, a recipient of the Superstar of STEM recognition, which is awarded by Science and Technology Australia. That program, the Superstar of STEM program, was initiated in 2017 to try to build a larger number of Australian women scientists, try to get a more equal gender balance between male and female among scientists and engineers in STEM fields. It's highly competitive, and congratulations to Karen for receiving that. As you might have seen from Karen's abstract, she is talking today about the relaxation of ensembles of magnetic nanoparticles, which, as she pointed out, can happen in two major ways. One is the physical rotation of some nanoparticles, or it can be due to the internal motion of magnetic dipoles within individual nanoparticles. This is a bit of a tricky theoretical problem, the solutions of which I can say with confidence have applicability beyond this particular problem. As Karen pointed out in the abstract, work on magnetic relaxation times in in non-equilibrium thermal physics were carried out as early as the 1920s by Debye. So it's a long-standing topic of interest. So Karen's talk today is entitled Magnetic Relaxation Times for Magnetic Nanoparticles. Thanks, Karen. Over to you.
Thank you, David. That was a lovely introduction. And I think you've covered some of my talk topic as well by covering so much. That's awesome. So thanks everyone for joining. This is a new talk for me. I was telling David and Murray before we came online that I'm used to talking to general audiences most recently. So to have the permission to give a talk with maths in it is quite different and a joy. And I hope you still think it's a joy at the end when you've seen some of the equations coming your way. Saying that, most of it will be explained with pictures. There's just a few equations in there. So this is work that was done at the University of Colorado at Colorado Springs, mainly funded through the BioFrontiers Center there. And also, since I joined the University of Newcastle, some of it's been done here as well. And I do want to acknowledge before I go too much further that there were 2 PhD students working with me who did a lot of the work that I'm going to be talking about. One of them is Artek Chalafor and the other one is Jonathan Davidson. And there were also 2 colleagues, Mus Crawford at the University of South Carolina and Nicholas Anderson. They were also heavily involved in this work. Okay, so we're going to talk about magnetic nanoparticles. So here's a really simple picture of a magnetic nanoparticle. I've drawn a ball here, and that's my theoretical physics view of a nanoparticle. It's a perfect sphere, obviously, and it's this gold color represents the magnetic material. Around the edge of it, we've got all these hairs. These are ligands or surfactants, which are used to stabilize these particles when they're in fluids. We're going to largely forget about those hairs from here on out. There's some really interesting physics to be done with the hairs, but we're going to leave them out in this physics talk. Now, the size of these magnetic nanoparticles, the core is roughly 10 to 100 nanometers in diameter, depending on the application. We're going to be in the lower end of that, say 10 to 30 nanometers wide. And that's a special size because it's a stealthy size inside the body. These particles can get inside the body and do something interesting without being detected by our immune system. So that's one reason this is an interesting size. The other reason it's an interesting size is because when we have such small magnets, the atomic dipole moments all line up inside this material, and we can represent the magnetization as a single vector. So I've drawn this blue arrow. This is the magnetization, or the magnetic moment for the nanoparticle. And I've put a north pole and a south pole so that we remember this is a magnetic system. Okay, so this is our picture. We're going to have a lot of pictures of balls with arrows in it, showing the magnetic nanoparticle and the magnetization within it. This is an approximation to say that we can represent the magnetization as a single vector, but it works pretty well in most situations. Okay, so we're going to talk about magnetic relaxation. So what do I mean by that? So say we take an ensemble of magnetic nanoparticles. I've just drawn 7 here, but imagine there's many thousands of them, as is typical in a solution. And if there's no fields on, then all of the magnetic moments point in random directions. But if we put on a field, then some of those magnetic dipole moments want to align with the field. They feel a torque and they want to align with the magnetic field. So you can imagine at some later time, after a field's been turned on, we have some alignment of the magnetic moments. Now, you might think that all the moments would want to fully align with that field and point upwards, but that's not what actually happens because these are highly thermal systems. So in actual fact, the magnetic dipole moments are moving around all the time due to magnetic fluctuations, and they don't perfectly align with the field. Only if the field is a really, really large field can we have that alignment. The reason they're so thermal is because of their size. So because these are such small particles, we have all the intrinsic magnetic energies are comparable to the thermal fluctuation energy. Okay, so that's the picture of magnetic relaxation. And if you've got that in your mind, then you're pretty much 80% the way through understanding the talk. And so just to reiterate, at our initial time, we can say that the net magnetization is 0 because there's no preferred direction. And then later, after we've applied the field, we have some net magnetization upwards. So we could make a little sketch of what we would expect the magnetization to do as a function of time. And I've got that on the next slide. So here's my sketch. Here's the net magnetization as a function of time. I start off at 0, and then I have this increase towards some saturated state or some equilibrium state. But it happens quite slowly. And you'll notice that that time to approach, or that approach, looks like an exponential approach. In most situations, it is exponential. And if we have that exponential approach, we can add on what we call a characteristic time. I'm calling it the relaxation time for the magnetic system. So it's that relaxation time that I'm interested in calculating. And it's important to calculate for a number of different reasons. So this brings me to the why do we care slide. Why do we care about magnetic relaxation times? Well, these magnetic nanoparticles are used for a variety of applications in industry and in biomedicine. And rather than list off all those different applications, you can ask me about them perhaps in the question time, but I'll give you one example that I've worked with. And that example is from biomedicine, and it's a treatment known as hypothermia treatment. So for example, if we have a tumor, say it's a brain tumor, and it's very hard to operate on, one way we could treat it is by actually raising the temperature of that tumor by a couple of degrees Celsius, and that will actually start initiating cell death. So magnetic hypothermia is using magnetic nanoparticles to induce that increase in temperature and help treat cancerous tumors. So I have a little bit more information on how that actually works. So if you have an oscillating magnetic field, an AC field, then the particles move, magnetic nanoparticles move in that field. That means that work is being done on the particles, and that work can be transferred to heat. So that's the principle behind applying fields to magnetic nanoparticles and getting out heat. So I've actually got a video over here of a simulation we did. This is an oscillating magnetic field, is the blue arrow, and we've got one single magnetic nanoparticle, the ball with an arrow, and we'll watch what it does as the field oscillates, if I can get it started. Okay, so you see as the field switches, the magnetic moment switches, and so we're doing work on that particle. And as I said, the work can be transferred as heat. This isn't just in the realm of experiments or theory even. This is actually an application that is used clinically in Germany. This company, Magforce, has this rolled out in 8 different hospitals in Germany. And these little vials at the bottom are actually their magnetic nanoparticles, which are iron oxide in a fluid. And this here is the treatment bed. So a patient would actually lie on this treatment bed. The magnetic nanoparticles are inserted into their tumor site. And then this large machine here is applying the oscillating magnetic field to the particles. And it's showing some success. And I can talk more about that again in the question time if anyone is interested. But this is just by way of motivating why we're worried about magnetic nanoparticles and how long it takes them to relax in a field, because it's the very mechanism by which hypothermia works. We want to make sure that those particles have maximum work done on them. So we want to make sure that we give them in the oscillating field enough time to respond to that field. Okay. Are there any questions before I keep rolling through? It's a bit funny to talk to no one, essentially. Are there any questions before?
It's really terrible. I think what we usually do is get people to type their questions in the Q&A.
Okay.
And then we ask.
Nothing yet?
No, nothing yet. I mean, it's not as bad as trying to tell jokes to a blank audience. That's even harder, right?
Okay, well, if there is no questions yet, I'll keep going.
All
But
right.
please do yell out if you've got something, so it's a bit more interactive. Okay, so David's already mentioned that there are two mechanisms by which magnetic nanoparticles can typically relax. And I'm going to talk about both of them in some detail before I get to the calculations that we've done. And the hint to what these relaxation mechanisms may be hidden in this video we've already seen. So if we watch the video again, we can see that the particle is jiggling. Okay, that's the technical term, jiggling. And also the arrow is moving independently of the particle as well. And that gives a hint to the two mechanisms. The jiggle is known as Brownian motion or Brownian relaxation. And the arrow moving independently, the magnetic dipole moment moving independently, is known as Néel relaxation. So let's start with the Brownian relaxation. So in this case, as I mentioned, the whole particle rotates. So to try to show a time series of this, say we've got a particle with the moment down at the start, and we put a magnetic field upwards, as shown by this red arrow, then over time, if there was just Brownian relaxation, the particle would rotate. And that particle brings the magnetic moment around with it for the ride. Now, there's something in this picture that I haven't explained to you yet, and I need to explain to you. There's this dotted line here that I've added to my particles. And this is known as the easy anisotropy axis for a magnet or for a magnetic nanoparticle. This is the direction in which the magnetic moment likes to lie. It's the preferred direction for the magnetic moment to lie. And the origin of this, the physical origin of this, is in the magnetocrystalline interaction. So the crystal structure gives us a preferred magnetization direction. It can also be due to shape of the particles, but because we're considering spheres here, it's really just due to the magnetocrystalline interaction. So I'm going to draw these lines a lot. All you need to think about with these easy axes is it's the direction the moment likes to point along. Okay, as simple as that. And so here, the moment is kind of locked to this easy axis, and the whole particle rotates into the field direction. There's some torque on the moment forcing it to align. This is called Brownian relaxation. It was named, many of you will know this, it was named after a biologist who worked in the 1800s, Robert Brown, who first noticed, I think it was pollen under a microscope was jiggling in a fluid. And so this refers to both rotations and translations of objects. It's been known about since the 1800s, and Debye did some interesting maths with it, including this nice book written in 1929 or published in 1929. Okay, what else can I tell you about this? Well, here is Debye's formula. This is a picture of Debye, not Brown. I wasn't going to put a biologist in my talk. So this is Debye, and he came up with this expression for the characteristic Brownian relaxation time, tau subscript b. And it depends on the viscosity of the fluid eta. It depends on the hydrodynamic volume of this magnetic nanoparticle with the hairs on it. It depends on temperature and Boltzmann's constant. Okay, so this is a well-known result for estimating the characteristic time it takes this ball to rotate. Okay. Oh, I see there's something in the chat. Let's see. Oh, that's okay. Yes, I'm open for questions. Okay, let's go to the other relaxation mechanism, and this is Néel relaxation. In this case, the particle remains stationary, and it's the magnetic moment that is dynamic. So if this is my start, it's a very similar picture to what we saw before. I start with my moment downwards. I apply a magnetic field upwards. This time, the particle is stationary, so that easy axis stays where it is, and the magnetic moment goes for a little excursion until it's pointing more or less upwards. Okay. Rather confusingly, the person who did the most work in this field was someone called Brown in the 1960s. So that's a little bit unfortunate because we've got Néel and Brownian motion, and the person who made a big contribution to the Néel relaxation was Brown. Okay, so this confuses students the world over, and not just students. So Brown studied it in the 60s and made a lot of headway, and we've really just built on his work from 1963. Okay, because of this easy axis that I've talked to you about, because there are two directions which are preferred, up and down, the magnetization actually has an energy barrier to overcome to do this reversal, to do this relaxation. So this is an energy barrier problem. And so here I've plotted out, or I've sketched the energy of a magnetic nanoparticle as a function of the angle of the magnetization. 0 is up and pi is down, okay? And we have two energy wells because both up and down along this easy axis direction are preferred. But you'll notice that the up well is slightly lower than the down well. And that's because we've got this field providing a bias. Okay, so the magnetic field means that the magnetization pointing upwards is actually preferred to downwards. But you'll see here's the barrier I was talking about. So whether we go over the barrier or not depends on how large that barrier is, that energy barrier is, compared to the thermal energy kBt. Okay, this is an animation a student of mine put together that I quite like, and I might have to run it again after I've explained what we're looking at. This is just 5 instances of looking at identical magnetic nanoparticles relaxing in a field. All right, so let me see if I can play it again. So each one is just a different instance where the thermal fluctuations are different, but everything else is the same. And you can see that the dynamics are vastly different for the 5 different particles. And that is because each of them feels different thermal fluctuations. And then he stopped the videos when he thinks that the particles or the moments are roughly pointing upwards. And you can see that time it takes to relax varies from, say, 3 nanoseconds all the way up to 28 nanoseconds. So there's really a variety of different behaviors. So we have to average over an ensemble to see what the net relaxation looks like. Okay, so this is a highly thermal, highly stochastic process. We need to do large-scale averaging to see what the relaxation time actually is. So as I mentioned, a lot of work was done by Brown in the 60s, but it is called Néel relaxation, named after Louis Néel, who did some work even earlier than that. And the Néel relaxation time is given by this formula here. There is I've just got to plug my computer in, excuse me while I do that. It's given by this attempt time, tau naught, and then an exponential factor, which is very familiar for anyone who's looked at relaxation over an energy barrier before. And in the exponent, we have the barrier height, which is this capital K, capital V. This has to do with the anisotropy energy of the particle and the volume of the particle. And on the bottom line of the exponent, we've got thermal energy. So this is mirroring what I was saying earlier, that whether we relax over the barrier depends on how tall the energy barrier is compared to the thermal fluctuations. All right, so this is our go-to formula for Néel relaxation. So what's new? I've given you a long introduction to magnetic nanoparticles and how they relax. What is new? Well, let me go back to these 2 formulas. the one that's commonly used for Brownian relaxation and the one that's commonly used for Néel relaxation. And what you'll notice is that both of these relaxation times don't depend on the strength of the magnetic applied field, okay? And people in my field of research in working with magnetic nanoparticles use them all the same. But you can imagine that the larger a magnetic field that you apply to the system, the quicker those magnetic nanoparticles can respond, okay? It makes sense. You put on a bigger torque, you put on a bigger force, the system should respond more quickly. And that is missing in these formulas for the relaxation time. So our goal was to go beyond these formulas and get to expressions for the Brownian and Néel relaxation times that was still easy to use, because otherwise experimentalists and clinicians won't use them, that is still easy to use, but include the effect of the magnetic field strength. Okay, so that was our goal. And we got there. Firstly, for the Néel relaxation time, we had a paper come out in 2021 talking about how we can extend this to applied field strengths. And a paper is about to appear either tomorrow or Monday, looking at the Brownian relaxation time and how we can extend that to include applied field strengths. So I'm going to talk to you about the older paper first, and then if we have some time, talk about the Brownian one that's just appearing this week. Okay. Any questions before I keep bulldozing on?
I think we're good.
Okay. All right. Good. Okay. Let's talk about deriving the Néel time. So just to remind you, the picture here is we have some magnetic moment. That's this little arrow here. It can lie on a sphere because it has a constant magnitude, and it's going to move like we saw in those animations previously. If there was no thermal fluctuations, it would actually precess, but because we've got thermal fluctuations, it can move all over the place. So the magnetization or the magnetic moment, M, depends on which particle we're looking at, and it depends on time, okay? Right, we can describe that motion, or we can calculate out that motion of a magnetic moment using the stochastic Landau-Lifshitz-Gilbert equation, which I've written here. But don't worry, I'm going to put some describers on this formula. So M is our magnetization, as I said. So dm on dt is describing our magnetization trajectory. This gamma here is the gyromagnetic ratio. And then if you just look at this first cross product, the cross product is with a functional derivative of an energy with respect to the magnetization. This is an effective magnetic field, and it's due to both the externally applied field and any other energies in the system. So this derivative here represents an effective field, and the M cross H, or the M cross field term, is giving us a torque. So this is the typical precession we see of a magnetic moment in a field. So to put it to something that you would have studied before, when you do your quantum mechanics study, you talk about L'Amour precession. You put a spin in a field and you see it precess. That is identical to this term here. Our next term is a damping term. So this is magnetic damping, the fact that energy is constantly leaving the magnetic system. And then here we have some stochastic thermal magnetic fields. So this is playing the role of temperature. This is giving us our thermal fluctuations in the system. And the statistics of the thermal fields are such that we recover the correct temperature, and we also have damping in there because it must obey a fluctuation dissipation theorem, okay? So this is our stochastic LLG equation. Without the thermal piece, it's just the regular LLG equation, Landau-Lifshitz-Gilbert equation, but with the thermal piece, it takes on this stochastic nature. Okay, so that describes the motion of the magnetic moment in every single one of the particles. So again, I've got lazy and I've just drawn 3 here, but imagine there's thousands of them. And again, I've got a video here showing the trajectory of just one. Okay, let's see if I can get it to play again. Okay, so there's the trajectory of just one, but they're all doing their own thing. To get out an analytic relaxation time, I can't do this for thousands of particles and then average. That doesn't result in anything analytic. So what we're going to do instead is map this stochastic Landau-Lifshitz-Gilbert equation over to what's known as a Fokker-Planck equation. Again, people outside magnetism might have some recollection of this from a class or may have come across this term before, the Fokker-Planck equation. In magnetism, we can map that stochastic LLG equation over to this Fokker-Planck equation. But what it physically means, jargon's not so good, what it physically means is instead of writing each trajectory for each individual magnetization, instead, we try to write an equation for how the probability density evolves with time. So what do I mean by probability density? I've given it by this curly W here. The probability density is what is the probability of measuring a moment in some angular region at some given time. That's what I mean by probability density, okay? And that's more useful because I have one probability density that describes the trajectories of all the particles in my system. Okay, the way to do this transformation from the Landau-Lifshitz-Gilbert equation to the Fokker-Planck equation involves lots and lots of maths. I had a student who did this and he presented me with a summary, which was 35 pages long, of how you can track this over to this sort of Fokker-Planck equation. So I'm not going to go through all the steps, unsurprisingly. The Fokker-Planck equation is here for what it's worth. As I said, I thought I could get away with some maths in this talk that I would not normally put in the talk. So we have a rate of change of this probability density with time, and it depends on all sorts of things, but the one I want to point out is this curly V again is my energy of the system. So this term here is where all the real and effective fields are in the equation. And just to go back to physics for a second, it's by putting on a field that we drive the magnetic probability density to change. Okay, so this is the term driving us to some new equilibrium. All right. We can solve this mess of an equation in some special conditions and with some special approximations. One of the approximations is to assume that this probability density evolves with an exponential dependence on time. And that's maybe not so surprising because we talked earlier, we had a little plot of how magnetization varies with time and it kind of looked exponential. So if we can put this kind of solution into this equation and crank the handle, do some maths, we can get out that this decay constant is P subscript 1. This is going to be the inverse of our relaxation time. So that's summarizing a lot of maths in some way. This is the term we're looking for, and then we'll have a feeling for our relaxation time. Okay, let's have a break from maths and go back to the physical system to make sure we understand what's going on. This here is a plot of the probability density as a function of magnetization angle, okay? And so theta being 0 is again up and theta being pi is down. And you'll notice that there is a peak in the probability density function at exactly pi on 2. And this is at some initial time where there's no field on and all the particles are pointing randomly. Their magnetic dipole moments are pointing randomly. So this probability density function is basically a sine theta function. It's saying that angles around the equator are much more probable than the two poles. And that's just because if I put a random distribution of angles or positions on a sphere, here I get this probability density function. So I hope everyone's clear on that. I'm saying with no magnetic field, I get a probability density function that's just peaked at the equator, and that's just because of geometry. There's much more chance to land on the equator than there is on the two poles. Okay. Once I put on that magnetic field upwards, angles near theta equal to 0 are going to be preferred. So what happens to my probability density function is it should move towards the pole. The area under the curve still has to be 1 for it to be a good probability density. So this is the evolution that the Fokker-Planck equation is trying to describe, from a symmetric peak around pi on 2 to something that is shifted towards the pole. Okay, I find this useful, more useful than the equation, to describe what we're trying to do. And then the characteristic time to go from this to this is what we're trying to solve for. Okay. So let me step back and say, well, again, this paper by Brown in 1963 did this sort of calculation, came up with this Fokker-Planck equation and solved it and got a characteristic time. But Brown did this by assuming a very special setup. He assumed that all the easy axes were parallel with the field. So this actually makes the problem much easier because everything is in the same direction. Magnetic field and anisotropy all lined up. So he looked at this reorientation of the magnetic moments in a field, but in this very special case. And he came up with a relaxation time, which is given by this mess. And you don't need to look at it too hard. The point is that he came up with an analytic estimate for the relaxation time, and it depends on field. And it depends on field through this little h parameter here, which is a normalized magnetic field parameter. So this existed in the literature from 1963. No one uses it, quite surprisingly, because it does have the magnetic field strength in there, and it is better than the simple Néel relaxation time. But it, as I said, is for this very special geometry. And this geometry is not really realistic because in reality, most of the time we have magnetic nanoparticles pointing in random directions, and the easy axes all pointing in random directions before we put that magnetic field on. So we wanted to go beyond this. And we wanted to go, as I said, from some random configuration of easy axes and see how they align with a field over time. And so Artek Chelafor, the student I mentioned earlier, really championed this, really did a lot of the work. And he followed the same method as Brown from 1963, but this time assumed that the easy axes were perpendicular to the applied field strength. This again is a high symmetry situation, so we can actually make analytic headway. We can get a pen and paper solution to that Fokker-Planck equation I showed you earlier. And the solution he came up with looks like this. Again, not really important. Don't worry about the details. But the key is that the magnetic field strength is in there. And we see that the relaxation time speeds up if we put on a larger magnetic field strength. Now, this special situation where the easy axes are perpendicular to the applied field, it's another simplified example, okay? It's another example which isn't quite the reality of random easy axes. But we claimed that this was a way forward because what we can do is say that if we have random easy axes, it's more or less equivalent to having everything pointing perpendicular to the field. And I'll explain that more in just a second. So wait for that. First, we wanted to test that Artek's expression was actually correct. And to do that, we compare the analytic expression we've derived to the results of simulations that we do. These simulations were for 5,000 particles. And I'll show you a plot here. This is one example of the magnetization of 5,000 particles. It's normalized as a function of time. And the blue dots are the simulation results. So the average magnetization as a function of time. And then we put a fit through this and pull out the exponential characteristic time, which is our relaxation time for the system. So if we do that again and again and again and again, we can compare to our analytic result. And here it is. So this is relaxation time for a system of nanoparticles as a function of temperature. The dots are results of those simulations that we did, and the lines are the analytic expression. There's two different field values considered here. One is 50 Ersteds and one is 200 Ersteds. But you can see for both cases, the analytic expression does a really good job at approximating what we get with the simulations. Okay. So that's really nice. That gave us a lot of confidence going forward that this was correct. Okay, so I claimed earlier that this gives us headway because we're going to say that the special case of easy axes perpendicular to the field is approximately equivalent to having random easy axes. The reason that is so goes back to something that I mentioned earlier, that if we choose a random ensemble with random easy axes, more often than not, those axes will be near the equator than they are near the poles, just from a probability point of view. So we claimed that this is a better approximation for a random configuration than Brown's case, where they're all parallel with the field. And we tested that out. So in this case, we have simulations again of the dots, and the dashed line is the analytic expression. And this time in the simulation, we've started with all the easy axes at random, rather than all the easy axes perpendicular to the field. And you can see that our expression still does a really good job at going through the dots. This is a logarithmic scale, so you have to take it with a grain of salt, because on a logarithmic scale, all the errors are shrunk down. So there are some errors here, but overall, it does a really good job. And as I said, the key point here is experimentalists are unlikely to run computationally heavy simulations to get out a relaxation time to see if their particles are suitable or not, but they will pick up an analytic expression and plug in their numbers and see what the relaxation time is and see if it's appropriate for a certain application. Okay, so in summary for that piece, and don't panic because I don't think I'm going to get through many more pieces in the allotted time. The summary for that piece is we have a new expression for the Néel relaxation time. It depends on the field strength, which it needs to for biomedical applications and industry applications too. And we have this realistic treatment of the anisotropy easy axes, which was largely missing until now. So this is a win. We've done lots of comparisons to simulations, as you've seen. It would be nice to have comparisons to experiment as well, but it's harder to do a comparison with experiment because it's harder to isolate that Néel relaxation from the Brownian relaxation. Okay, let me take a breath. I think I've got about 4 minutes left before we do some questions. So let me just go over the 10 remaining slides really quickly so no one understands what's going on. No, I won't do that. That's a joke. Okay, so let me just tell you very briefly about Brownian motion and then I'll show you a cool animation, and then I'll be done. Okay, so we've covered the Néel relaxation and how we've extended that and tried to make it more realistic. Now let's talk about the Brownian relaxation. You might remember this is the physical rotation of these particles. And this looks similar to a slide I showed earlier for the Néel relaxation. This time, what governs the dynamics of a single particle is actually Newton's second law for rotation. So we can write down a stochastic rotation equation to model how these particles are rotating in a fluid thermally. And then we can map what are individual equations for each particle. We can map that to the equation describing the evolution of some probability density. And we get to another Fokker-Planck equation. This one is actually easier, actually. There's much less maths involved this time in going from Newton's second law, which governs the motion of particles, to the relevant Fokker-Planck equation. Okay, it looks like this. I hope I don't lose too much of the audience by saying this is what it looks like. It's a little bit more obvious that this is a Fokker-Planck equation to anyone who's played with them before, because this term here is our driving torque. This is our particles trying to rotate to align their moment with the external field. That's this term here. We call that the driven term. And then over here, we have a term that depends on temperature. That's our diffusive term. Okay, once again, we can do some analytic approximations and manipulations to try to get out a characteristic time from this. And that's exactly what we do. Let me skip over that. And we actually get two characteristic time scales here. One is a diffusive time, which turns out to be exactly what Debye found in the 1920s. So this is cutting edge science right there. And the other one is a new term. This is our approximate time to relax due to the field. And we can actually combine those two times reciprocally. This is often done. And the reason we do it like this is because it mimics the idea that the fastest time scale wins. So we add the two times reciprocally to get the total relaxation time. And in the end, we get an expression that looks like this. And it's got the rotational viscosity on the top line. It's got KBT, the thermal energy, on the bottom. And it's got the magnetic moment mu multiplied by the magnetic field B on the bottom. This is our term that's driving the relaxation. Okay, so a really simple expression. We've made a lot of approximations to make it so simple. And let's compare it again to some simulations to see if it's any good. Okay, so here's the result. There's lots of lines on this plot, so let me take you through. This is the Brownian relaxation time as a function, this time of radius for the particles. The dots are our simulations. And then this dot dash line at the bottom is our expression that I showed you on the previous page. And you can see it doesn't do so well. All right, we've made a lot of approximations, possibly too many approximations, so that we don't do so well at mapping that relaxation time. Order of magnitude, it's great. The field dependence, it looks good, but it's a little bit lower than the simulations reveal. Okay, so we've made an expression that's analytic, which a lot of people don't have. It's simple to use, which is great, but you lose a little bit of accuracy by doing this. But the good news is that we can use this time to do subsequent calculations, and it makes those calculations much better. So I'm going to skip a couple of slides because I'm at 51 minutes past, so I think I should wrap up. So I'm going to skip some of these. And the last thing I want to leave you with is I've talked a lot about relaxation times due to Brownian and Néel, rotations and internal magnetization dynamics, but translations are also important. and they haven't been included in any of our analytic work, but we can include them in videos and simulations. So here's an example of an oscillating magnetic field acting on some particles. Translations are allowed in these simulations, and what you'll see is that the particles start to form little chains. And these will be, the formation of chains really change the relaxation dynamics and the response in a field. The particles get slower at responding to the field as they form longer and longer structures. So that's largely been left out of my discussion from today, but it's cool to think about as future work, and it also shows you a really nice video. Here's one more video before I go. This time the particles are being drawn down to a magnetic substrate. You see the Brownian translations and rotations going on as the particles move to the surface under the effect of large magnetic field gradients. Okay, thank you to all the collaborators. Thank you guys for coming and listening. And with that, I'll open for some questions, hopefully.
Thanks,
you.
Karen. That was really interesting. I love that last animation with the chains forming. That's just beautiful.
It didn't fit with the talk, but I thought I needed to put it in.
Oh, yeah. We definitely want to see that. In fact, I was going to ask a question about that. To what extent can you assume that the response to the external magnetic field are independent of each other? And the last slide answered that beautifully.
Yeah, so all the analytic work I showed, these particles are non-interacting.
Yeah.
And really, when they're in real systems, they often are interacting. And you can see with the translations, especially, how important that can be. Yeah.
I was talking to an economist once, and he said if physicists were doing agriculture, they'd be talking about spherical cows. Well, I don't see anything wrong with talking about spherical cows, but DC Lau wants to ask you, what if the particles are not assumed to be spherical? Would that make any significant difference to your results? Yes,
definitely. So firstly, the anisotropy barrier is very different because you have what's known as a shape anisotropy. Magnets like to have their magnetization lying along the long direction of a particle. And so the energy barrier for reversal will get much higher due to shape effects, and that changes everything, basically. So you have a different barrier height, and you also have a different energy landscape, which changes your relaxation dynamics.
Okay, so it could get quite a bit more complicated.
Yeah, the other thing that complicates it, is we have assumed what's known as uniaxial anisotropy. So up and down are equivalent, but many realistic materials have a cubic anisotropy. And only a few papers have started to consider that cubic anisotropy. So again, the energy landscape's much more complicated than we assume in simple pictures.
In that last animation where the chains were forming, is that because the easy axes are tending to line up, or is there some other physical phenomenon that causes that?
So this is because each one is a little dipole.
Yeah.
And so they will attract each other due to their dipole-dipole interaction.
Just lining up north-south like little magnets.
Exactly. To get such a large simulation to run with these many thousands of particles and translations and rotations, we've actually turned off those internal Landau-Lifshitz-Gilbert dynamics. So they've been turned off, and we assume that the particle's magnetization is locked to the easy axis direction here.
Okay, all right. So that clarifies that. Thank you. What were my other questions? See if anyone else pops up a question while I'm asking.
We've lost a couple of people, so they've obviously
that's okay. Sometimes
questions.
People have got lectures, they've got to chuff off for a 2 o'clock lecture or something,
Yeah.
But that's okay. They can catch up on the YouTube video. So one thing that interests me is these things for the nanoparticles that you're talking about. You said 25 nanometers, so somewhere between 10 and 25 nanometers. So I was just doing a quick mental calculation. What's that? 5,000 to 10,000 atoms, something like that. Would that be right? So in terms of Bohr magnetons, the spin of each nanoparticle could be something like 10,000 to 20,000 Bohr magnetons. Would that be roughly right?
Yeah, you're in the ballpark, yes.
Okay, so in theory, you should be able to detect a clump of these in the, for example, in the human body using external squid magnetometers, for example. I don't know if you know of any work where people are using magnetic nanopoles, perhaps aligning them with an external field and then doing imaging using that sort of technique. Is there any discussion about that in the literature?
So there are applications of magnetic nanoparticles as MRI contrast agents.
Ah, right. Okay.
Using traditional MRI, they've typically not been popular, and that's because of some negative contrast. So it's not a physics reason. It's very hard to change a clinical field and adapt a field because of this strange contrast. Now, alongside that, there's work at NIST in the USA looking at trying to make MRI operable at much lower magnetic fields. So currently the MRI we have in our hospitals in Australia operate between 3 Tesla and 10 Tesla, which are massive fields and really hard to generate. If you can get MRI to work at lower fields, suddenly it becomes cheaper, it becomes portable, it goes to less developed areas. That would be huge. Now, the reason we have these massive magnetic fields is because you're trying to align all of the hydrogen spins in the body.
Yeah.
So if you can put in these magnetic nanoparticles and they have a dipolar field and they're located next to one of those protons in your body, perhaps they give it a sufficient field strength that the proton is aligned and you can do some interesting MRI imagery that way. So there's some work using magnetic nanoparticles as the contrast in low field MRI, which is currently in the research stage.
There's another advantage too, I think, of trying to go to systems using lower fields. I remember there was some work being done at University of Berkeley a while ago showing that the resolution of MRI images could be improved, particularly for soft tissue imaging using lower fields. I don't know where that work went, but I remember it being done in the 90s.
Yep. There's another imaging technique which is relatively new, known as magnetic particle imaging. And I think there's not that many commercial machines operating. We have 2 in Australia. They're for animal studies, not for human studies at the moment. And again, it uses magnetic nanoparticles as the contrast, and it actually relies on the magnetic nanoparticles forming these little chains in order to get images which have a good enough resolution to be useful for diagnostics.
Okay, that's interesting. And then specifically for example, for cancer treatment, are there ways to, this might be outside of your talk, but you probably know, are there ways to encourage the nanoparticles by selection of the type of lipids that you attach to them to selectively target some cells rather than others, for example? I mean,
100%. There's different, we leave it to the chemists, but the coating is very important for targeting different cancer cells. And I don't know too many of the details, but I know, for example, I think there's some vitamin Bs that are preferentially taken up by cancer cells compared to regular cells. So yeah, you can coat it to try to get that preferential uptake.
Oh, fascinating. I mean, the work's got potentially very wide range of applications. And it was interesting theory too. So thank you very much, Karen. Let me just check. I don't think there's any more questions we've omitted in the Q&A panel. So let me just thank you once again. And I'll remind everyone that we'll send emails around for whenever the next talk is on. So everyone have a good day, and thanks, Karen.
Thank you.
No worries. Bye.